Hello my dear VLSI aspirants. Welcome to Deep Silicon VLSI YouTube channel. In this video, we are going to discuss about a question based on properties of XOR gate. Without any delay, let's start. If the input to the digital circuit consisting of a cascaded of 1375 XOR gates is X, then what is Y? Means they are expecting the output. What is the output? Guys, it is an XOR gate. What is a truth table of XOR gate? Whenever odd inputs are present, output is 1. Whenever both the inputs are same, then output will be 0. Like this, isn't it? Yes. Now, as per this, if you analyze this, XOR gate, if one of the input is logic 0, output is same as another input. Means it acts like a buffer. XOR gate can be used as a buffer by keeping one of the input as 0. Similarly, if one of the input is logic 1, then output is complement of the another input. Means XOR gate can be used as a inverter also, NOT gate also, by making one of the input as logic 1. Okay, so XOR gate can be used as a buffer, inverter as per the input. Now from this, guys, here you see for the first XOR gate, let's consider this is the first one, second one, and total 1375. So this is 1374 and this is 1375. Now guys, here 1x, if one of the input is logic 1, from this it acts like a inverter NOT gate, hence we get here x bar. Similarly, now x bar, guys, from the same table, if it is x bar, then you may get either this combination or this combination, because one of the input is 0, then another input will be 1, 0. Hence, guys, for these combinations, output is logic 1. Hence, if the XOR gate x bar x inputs, then output will be logic 1. Okay. So similarly, if you take the third one, third XOR gate, input is 1 and x, then what you will get? X bar only. Again, x bar and x, the fourth XOR gate, output will be logic 1. From this, what you can understand is, in this digital design, for the odd number of XOR gates, the output is x bar, and the even number of XOR gates, the output is logic 1. That's it, guys. So that you only tell me 1375, is it even number or odd number? Don't ask me. It is a odd number only. Hence, here for this 1375 odd number, the output is simply x bar. Okay, guys, this is what simply is like. We should not consider if there are 20 XOR gates or 19 or even let's consider 4 or 5 XOR gate. You should not do like a serial wise second gate output, third gate output, fourth gate output like that. No, not at all. This is a simple shortcut which saves your time. Okay, guys, this is what regarding the properties of XOR gate through a question. And apart from this, guys, you can note it down. What are the properties of XOR gate? Right? Now, let's see. Suppose if it is A XOR A, what we get, guys? Obviously, it is 0, because for the same inputs, output is 0 only. Hence, A XOR A, 0. Similarly, A XOR A bar, we already studied, that is 1. The same thing, guys, you can take the 0 here, you can send the A this side. That means here, A XOR 0, it acts like a buffer if one of the input is logic 0. Similarly, A XOR 1, it acts like an inverter, NOT gate, A bar. This one, guys, moreover, if you consider one of the input as complement, A bar XOR B, then what will be the output? You only write down. For example, if it is A XOR B, just for example, it will be like A bar B plus AB bar. Actually, in place of A, you should take A bar, no. Then in place of A, you take one more bar. Now, what you will get, guys? AB plus A bar B or A bar B bar means A XOR B. Right? It is applicable to another input also. If you take A XOR B bar, then also it is A XOR B only. Now, what if there are complements for both the inputs? Means A bar XOR B bar. Let's assume it is A XOR B. Then it is A bar B plus AB bar. Now actually AB inputs has complement, no? Then you apply complement for all the inputs, like for both the inputs. Then guys, what it is? A B bar plus A bar B means XOR gate only. Hence here what we can understand is, for an XOR gate, if one of the input is logic 1, it is a XNOR gate only. For both the inputs, if you apply complement, then it is still XOR gate only, XOR operation only. Moreover, guys, suppose instead of 1, they can ask you 0, or else they can give you X only. In such case, what will happen? That is, guys, let's consider A XOR A XOR A. Then guys, what it is? A XOR A, 0, 0 XOR A. Then obviously it is A only, means odd number. Similarly, let us take even number, A XOR A XOR A XOR A. Then what it is? This A XOR A will give you 0. This will give you 0. 0 XOR 0. For the same inputs, output is 0 only, na? Hence, output is 0. So with this, even you can give one more property, that is A XOR A XOR A XOR and so on n times. Then obviously, what is the output? If this becomes A when n is odd. Got it? Similarly, this becomes 0 when n is even, isn't it? From this is the one. And guys, here we can say even for this truth table, for the same, this entire setup for XNOR gate also. Yes, because this time they have asked XOR, next time they can ask you XNOR as well, isn't it? Yes. What about that XNOR gate? Okay guys, this is about like the properties of XOR gate, right? Now let's see regarding the XNOR gate. What is the truth table for XNOR gate? It is when inputs are same, output is logic 1. Similarly, when inputs are different, like 0, 1, 1, 0, output is 0. How we got this table? From the expression none other than A bar B bar plus AB. This one. As per this equation, we got this. This is the truth table. From this, what you can understand, when inputs, like one of the input is logic 0, then output is complement of the another input. Means XNOR gate can be used as a inverter when one of the input is logic 0. We can make in this way as well. Let's consider this is XNOR gate, and here if one of the input is logic 0, then output is A bar. Inverter, similarly, you take XNOR gate, make one of the input is logic 1. See here, if one of the input is logic 1, then output is same as, here it is 1. output is same as another input, that means it is used as a buffer. Hence here output follows another input like A. So this is what here the basic thing, when XOR gate can be used as a buffer, when XNOR gate can be used as an inverter, right? Now from this what you can formulate, that is, I mean to say properties. A XNOR A. Obviously guys, when inputs are same, output is logic 1. And obviously when A XNOR A bar, when inputs are different, then obviously 0. Now the same you can take A XNOR 1, you will get A only. If you move this to here, this can be moved here. Therefore you can write one more, A XNOR 1 is equals to A only. Even from this you can say, if XNOR, in XNOR operation, if one of the input is logic 1, then output follows another input buffer. The same way here also, A XNOR 0, it acts like an inverter, NOT gate, A bar. This one guys, these are the properties. Even if you perform A XNOR A XNOR A, what will be the output? A XNOR A will give you 1, and this again one of the input is logic 1, then it acts like a buffer, means it's A. Similarly, let us take A XNOR A XNOR A XNOR A, means even number. A XNOR A will give you 1, A XNOR A will give you 1, 1 XNOR 1, it is logic 1, hence it is 1. So from this you can give one more point, that is A XNOR A XNOR A XNOR and so on n times. Then obviously the output is like A when n is odd. Similarly becomes 1 when n is even. This is what regarding the properties of XNOR gate. Right guys, this is what here the properties of XOR gate and XNOR gate. Let's have a good numerical on XOR operations. Without any delay, let's start the question. Let x1, x bar, x2, x bar, x3, x bar, x4 is equal to 0, where x1, x2, x3, x4 are Boolean variables, and this is the XOR operator. Which one of the following must be always be true? Guys, these are the options. See, if there are 4 variables, then how many combinations we get in the truth table? 16, because 2 power number of variables will be the total number of combinations for a truth table. Now this x1, x2, x3, x4, let's assume the output is y. Okay, now the inputs, it could be 0 0 0 0 to 1 1 1 1. Okay, now let's see here, if the variables are 4, the inputs could be either from 0 0 0 0 to 1 1 1 1. Guys, here you see from the options x1, x2, x3, x4 is equal to 0. How this is correct? When inputs are all ones, let's take one combination. When all the inputs are 1 1, then is it true? No, because 1 into 1 into 1 into 1, then it is 1 only now, it is not 0. Even you take 1 1 1 1, which satisfies this condition, because 1 XOR 1 0, 1 XOR 1 0, 0 XOR 0 0 only, but still this condition is satisfied. Hence we can say this is false. For the input combination 1 1 1 1, even for some of the combinations as well, you will get like the output as 1 also. It is not like always it is 0. Similarly, you take this x1, x3 plus x2, 1 into 1 plus 1, you will get 1 only now. Hence, this is also false. You can take few more combinations also, but even for one combination, if it is not valid, then that will not be the answer. Now even you take the fourth one, x1 plus x2 plus x3 plus x4, 1 plus 1 plus 1 plus 1, then it will be 1 only. These are logical additions. Hence, this is also false. Okay guys, now you take the third one, x1 bar, x3 bar. It is like 1 bar 0 XOR 0, 0 XOR 0, 0 only. Similarly, x2 bar 0 XOR 0, 0 only. Yes, here this condition is satisfied for even 1 1 1 1 combination also. Even you can ask me, sir, for 1 1 1 1 it is like satisfied, but what about the remaining combinations? See, here for one combination it is true, but he cannot give you the guarantee. For that reason, you can go in another way also. What he told, that is x1 bar x1 XOR x2 XOR x3 XOR x4 is equal to 0. Now you take x1 XOR x2 XOR x3 XOR x4 is equals to 1, right? Now here, why don't you change this interchange? Why don't you interchange this? Because for XOR gate, commutative property is allowed. Hence, it is x1 XOR x3 XOR x2 XOR x4 is equal to 0. Now guys, here what we can say is this x1 XOR x3, isn't it? Here for the two inputs, let's consider this. From the properties of XOR gate, if you apply complement to both the inputs, still it follows XOR operation only. Hence, you can rewrite it as x1 bar XOR x3 bar. Similarly, x2 bar XOR x4 bar is equal to 0. Now you move this term to that side and you move x0 this side, then it is x1 bar x3 bar XOR 0 is equals to x2 bar XOR x4 bar. Now guys, we know very well XOR gate can be used as a buffer when one of the input is logic 0. Now here this x1 bar XOR x3 bar whole XOR 0 is x1 bar XOR x3 bar is equals to x2 bar XOR x4 bar. This one. Hence this condition is true as per the given statement. Hence we can say option C is the right answer. We are going to discuss about minimum number of NAND gates, especially at implementation level. Without any delay, let's start the question. The minimum number of two input NAND gates required to implement the Boolean function Z is equals to A, B bar, C, assuming that A, B and C are available. Guys, usually, like before going to take this question, you should you need some foundation. Yes, what is that? Usually the expressions could be either SOP or POS. Let's consider SOP, the expression y is equals to AB plus CD. Then this can be implemented in terms of AND OR levels, isn't it? Let's consider this ABCD, one AND gate, again one more, and these outputs are connected to a OR gate. Then this will be AB plus CD, isn't it guys? This AND OR implementation can also be represented in terms of NAND gates. Yes, how? You take here the bubble, here also you take the bubble. then nothing will happen. You are not going to change the actual implementation, right? Because a bar whole bar is a only. And here you take this particular bubbled OR gate. This is a bubbled OR gate. It can be represented as a NAND gate. We know alternative symbols. Hence, you can take this as like this. Now the design is in terms of NAND gates only. Okay guys, here it is like AB, CD, and output will be like AB plus CD only. So from this, what you have to know is a design in AND OR level implementation, the 2-level implementation that can be replaced by NAND implementation, right? This is what the point. Hence, AND OR implementation can also be implemented by NAND, right? Now, you see here regarding even POS also, if it is y like y is equals to a plus b into c plus d, the POS expression. For this you want to implement, then we need OR AND implementation. First you need OR gates, and these outputs are connected to an AND gate. This one, this OR AND also can be replaced by NOR implementation, right? So for this you can refer the short which we have given already in our YouTube channel, right? Now guys, here you take this expression. What is this expression? Is it an SOP expression or POS expression? It is a POS expression because A into B into C, isn't it? So it's like a product of sum and like this. Okay guys, now here usually what we have studied is AND OR implementation can be implemented by NAND and OR AND implementation can be implemented by NOR. But the given question is in a POS format, but he is asking the 2 input NAND gates. Then how come it is possible? It is one of the best question that you need to consider. Yes, then how it is possible? Guys, as per the expression, suppose if I want to implement using NAND gates, you can take one input where here this is AC, and if I have the B bar, let's assume, then I'll get here the output as AC into B whole bar, B bar, right? AC into B bar whole bar. For this, if you consider a NOT gate which acts like a NOT gate, this is a NAND gate only but acting like a NOT gate, then you will get A B bar C only, because AC B bar whole bar will give you the same A B bar C. Now this is the one. Then how come you get AC? For this, here we can take one NAND gate whose inputs are AC. Then I'll get AC whole bar. Again you take one NAND gate which works like a NOT gate. Therefore, we will get AC only because AC bar whole bar. Again here B bar. You take the input B. Again NAND gate which works like a NOT gate. This one. So that guys, here you get it. So this is the implement, like you can implement the POS expression in terms of 2 input NAND gates. See here. Now guys, tell me how many minimum number of 2 input NAND gates required to implement this function? Obviously 1, 2, 3, 4, 5. 5 is the right answer. With 5 2 input NAND gates, you can implement the given function. Right guys, here whatever I have told, all these are very important things, and this is the peak of the subject. Right guys, like this is what regarding the two input NAND gates implementation. We are going to discuss about the implementation using two input NOR gates. That's it. Without any delay, let's start. What is the minimum number of two input NOR gates required to implement the Boolean function y is equals to AB plus C? Guys, we already have given the link related to foundation for this particular question in the description. You can check it out. From that, what we can conclude is an expression which is in the SOP form can be implemented in AND or NAND. Okay? Similarly, POS expression which can be represented in OR AND or NOR. For more details, you can check the link which is available in the description. Now coming to the point. Here, the given expression is AB plus C, which is in the SOP form. But the twist in this question is they are asking in terms of NOR gates. Usually, if it is SOP, you can represent in terms of NAND. But here you need to consider NOR gates. That's it. Okay, let's consider the question AB plus C. Here guys, as per the distribution theorem, you can write this y is equals to AB plus C as like this. That is A plus C into B plus C. Okay guys, when C is common, you can take C plus AB. Still you have a doubt. Let's check. This is A into B, AB, A into C, AC, BC plus C. Now guys, here C is common. AB plus C into A plus B plus 1. 1 plus anything, 1 only. Then it is AB plus C only, no? By using distribution theorem, you can rewrite the AB plus C as A plus C into B plus C. Now you got POS expression. Now you can implement easily. Yes. Now let's consider from the OR AND. It is one expression which is implemented in the OR AND level. Let's assume this is A, C. And this will be like B, C. This will be A plus C. This will be B plus C. And now these outputs are connected to a AND gate. Hence, y is equals to A plus C into B plus C. Isn't it? Yes. But here the question is two input NOR gates, and we only told OR AND implementation can be done by NOR also. How? Let's take here two bubbles. Therefore, nothing will happen to the implementation because a bar whole bar is A only. Now here this particular bubbled two input AND gate. This is a bubbled two input AND gate. Can be represented as NOR gate because same only. And for this particular alternative symbols which we have explained already in YouTube shorts, you can check it out. Okay, now coming to the point. Here this particular initial gates as usual, this and this. And these outputs are connected like this. It is AC, it's BC. You got here A plus C into B plus, here A plus C, here B plus C. It is a two input AND gate only, this NOR gate. Hence, you will get output Y as A B plus C, which later can be expressed as A plus C into B plus C. It is a SOP expression implementation using NOR gates. Of course, 2 input NOR gates. This is the one. Now finally guys, how many 2 input NOR gates required to implement the expression Boolean function y equals to AB plus C? None other than 3. 1, 2, 3. Right guys? This is what here the implementation of SOP expression in terms of NOR gate. Let's enter into the question without any delay. A circuit outputs a digit in the form of 4 bits. 0 is represented by 4 zeros, 1 is represented by 3 zeros and 1. And similarly 9 is represented by 1001. Means simply it is decimal to binary using 4 bits. A combinational circuit is to be designed which takes 4 bits as input and output as 1 if the digit is greater than or equals to 5. This is the design requirement and 0 otherwise. Okay guys? If only AND, OR and NOT gates may be used, what is the minimum number of gates required? It is about implementation by simplifying the design requirement. You should not take the design requirement as it is and implementation. VLSI means real estate. You need to implement the design in less amount of hardware, in less amount of space. That's what in a simple, like in lucid language I can say. Now here guys, as there are 4 bits are present, how many combinations we get? 16 combinations. If you write the truth table from 0000 to 1111, you can write down even inputs are like 0100, outputs are zeros only. From 0101 onwards till 1111, output becomes 1, right? As per that, if you write down the truth table, I mean to say K-map, then it will be like this. You know very well guys regarding the 4 variable K-map. So here it will be like this. It is like A, B, C, D and it is A bar, B bar, A bar, B, A, B, A, B bar. Similarly, C bar, D bar, C bar, D, C, D, C, D bar. Now, you know very well the decimal representation, if you say it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? Now, if the digit is greater than or equals to 5, output is 1. Means from 5 onwards, like 1 only. This one. Okay. Now, we want to simplify the design. Remember. VLSI means real estate. Again, I am telling you. Now, how you can simplify? You can take here 1 octet. Therefore, it is B bar gets cancelled. All the terms gets cancelled. It is A. Similarly, here 1 quad. Therefore, it is A bar gets cancelled. C bar gets cancelled. It's BD. Similarly, there is another like quad here. That is BC. This one guys. Hence, the simplified expression for this particular design requirement is, let's say y is equals to A plus BD plus BC. Even you can take common the B, then it is C plus D. A plus B into C plus D. And what are the gates available? Here they told we need to implement using these gates only, AND, OR and NOT. And of course you don't require any NOT gate. Hence here if you implement, it is like C plus D, you require one OR gate which can give you the output C plus D. And you can give the same to one AND like a AND gate, so that you will get it as B into C plus D, and this will be given to again one OR gate. Let's say this is A, and here we have given to one OR gate, and this will be Y. Hence guys, how many gates required? 1, 2, 3. Hence the right answer, what are the minimum number of gates required, is 3. Okay, even guys, you might get it out, sir, I don't want to take the common, I want to write A, B, D plus B, C only. Then for this you require one OR AND gate, for this you require one AND gate, but still to OR all these like terms you need OR gate. No, of course that time you require 3 input OR gate, right? Usually you need to consider minimum number of inputs, that like whatever the logic gates, right guys? This is about the simplified implementation as per the design requirement. It is a simple example, greater than or equals to 5. In your journey you may get different kinds of design requirement. I have the like input, I want square of the input, there is a BCD data, I want to implement in a gray code, like that they'll say. See, these are all and all regarding the design requirement. As per the design requirement, we need to implement the simplified design. We are going to discuss about calculation of inputs for a given output expression. Yes, without any delay, let's enter into the question. The circuit shown below is to be used to implement the function z is equals to f of a comma b is equals to a bar plus b. What are the values of I and j? This is the given design. They have given the output expression and we want to determine these I and j values as per this Boolean function. So I repeat, z is equals to a bar plus b. Guys, here if you take this OR gate, the output term will be a plus I. Similarly here, a bar plus j. Now the actual expression for this AND gate, z is equals to a plus I into a bar plus j, isn't it? Yes. Now guys, you compare both the expressions. This is the obtained expression and this is the required expression. How you can get it the same? Whenever I is equals to 1, so that anything plus 1, 1 only, 1 into anything only. Moreover here a bar plus b na, so in place of j, b is required. Hence you can say j is equals to b. By substituting these I is equals to 1, j is equals to b in this expression, the expression will be like a plus 1 into a bar plus b. Therefore guys, the final expression is a bar plus b. Hence LHS RHS are equal. The obtained expression, the required expression are same. So in this way you can determine the inputs for the given output expression. Okay, let's see another model. What is the required input condition a comma b comma c to make the output x is equals to 1 for the below logic circuit? Here also the same. They are expecting the output to be 1. What are the input combinations? What might be the a value, b value, c value? That's it. Now guys, here as per the design, what is the expression here? It is an XOR gate. Therefore, it is a XOR b. Similarly here, b, c. It is XNOR gate. Therefore, b XNOR c. And it is c. Therefore, the actual expression for x is equals to a XOR b into b XNOR c into c, because it is AND gate. Now here, what is b XNOR c? BC plus B bar C bar, XNOR expression. Therefore, here it can be like BC plus B bar C bar. Again guys, C. Now, if you multiply, what we get? BC into C, BC. C bar into C, 0. Then it is A bar B plus AB bar, the XR output expression, into BC. Hence again here guys, A bar BC, A bar BC. Again, B into B bar, 0. Then it is A bar BC. So the output expression is A bar BC. Now here, if A is equals to 0, so that 0 bar, 1, B as 1, C as 1, then obviously output will be 1. For this condition only, for this combination only, output will be 1. This is method 1. Yes, the regular approach. However guys, to optimize the time, to save the time, we have another method. That is very simple. In fraction of seconds, we will get it. Let's see. Now, guys, output to be 1. Then for a AND gate, all the inputs must be 1, right? Then only I will get 1, no? Right. So, C as 1. For this XNOR gate, for whenever the input combinations are same, then only output will be 1, no? For 0, 0 combination or 1, 1 combination, you will get the output as 1. But here C must be 1. Then obviously B must be 1. Then only B XNOR C will be 1. Now, guys, here, this is XOR gate, this is XNOR gate. Obviously, for the different input combinations, output will be 1. Hence, here A value must be 0. Therefore, A0, B1. You will get output as 1. 1, 1, output as 1. 1 anyway. In this way also, you can tell the input combinations for a given output. Remember guys, for every problem in life, in the design simplification, there will be multiple solutions. Which solution you have considered is you only. Okay guys, this is about like the determination of input combinations for a given output. Let's have another design challenge. That is, the output Y in the circuit below is always 1 when 2 or more inputs PQR are 0, 2 or more inputs PQR is 1, any odd number of inputs PQR is 0, any odd number of the inputs PQR is 1. For which combination the output will be 1 for this design. Okay, usually what we do is, for this we will calculate the actual Boolean function, Boolean expression. Accordingly, we will choose the options, or we can see the design requirement for which condition output will be 1, like that. But however guys, with a simple shortcut, you can finish this question in fraction of seconds. Yes, how it is possible? Guys, here, if you observe this part of the design, you can understand this is a NAND implementation, isn't it? If it is a NAND implementation, it can be expressed in SOP form. Therefore, what is the output expression here? It is PQ plus QR. We know already, even we have given link in the description guys, how NAND implementation gives you the SOP expression. Okay, now here this is a NOT gate. Please don't think it is some other gate. It is a NAND gate only, acting like a NOT gate. Okay, therefore it is PQ plus QR whole bar. Now guys, what is this NAND gate output? It is Q and it is R, then it is PR. It's P, right? R. It's a PR whole bar. Now guys, what is the output expression Y? It is PQ plus QR whole bar into PR bar whole bar, because it is a NAND gate. By using De Morgan's theorem, if you simplify, you get PQ plus QR whole bar plus PR bar whole bar, and you know A bar whole bar is A only, hence it is PQ plus QR, again here plus PR. Finally guys, for this particular design we obtained the output expression PQ plus QR plus PR. Yes, for this given Boolean function, what might be the truth table? Because they are expecting the output to be 1. For which conditions? If you want to know the conditions, you need to draw the truth table. There is no any other way. Hence guys, here we can say PQR and the output is Y. You know, for there are 3 variables, we will get 8 combinations: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, if you take PQ plus QR plus PR, now this is 0 into 0, 0, 0 into 0, 0, 0, 0 into 0, 0, 0 into 1, 0, 0 into 1, 0, 0 into 0, 0, 0 into 1, 0, 1 into 1, 1, again 1 into 0, 0, therefore 0 plus 1 plus 0, it is 1. Again here, when you perform as per this Boolean expression, you will get the expression as this. Okay, now you see when output is becoming logic 1, for this case here, here, here. So output is 1 when 2 or more than 2 inputs are 1. In such combination only you will get output as 1. Hence guys, here you can say the right answer is 2 or more inputs PQ are 1. In this combination, for this situation only, output will be 1. Right guys, this is what another design challenge. You need to know the logic optimization in VLSI. That is very, very important, and of course this itself you do when you enter into VLSI industry. Let's have another design challenge. For the logic circuit shown in the figure, what is the output Y? So this is a given design and they are expecting the output Y value. What is that? Now, if you want to find out this, you need to know the outputs of these 2 gates. Similarly for this one, hence let's consider this as P, Q, R, S. Okay, now guys, here coming to the Y, what is Y guys? It is R plus S whole bar. Coming to S, it is simply Q plus C bar whole bar. Again here R, it is Q into B whole bar. Similarly Q, it is P into B bar whole bar, and even you can take P, which is AB whole bar. This one guys. Now let's simplify this P. What it is? A bar plus B bar using De Morgan's theorem. Now substitute here, it is A bar plus B bar into B bar whole bar Now what we get, guys? You will get even, see, AB bar whole bar, if you take also, you will get it AB into B bar, it's 0 only, because B into B bar. Now if Q is 0, then what will be R, guys? 0 into B, 0 bar, 1, R as 1. Similarly, what is S? Q is 0 plus C bar only, C bar whole bar, C only. Now the S is C. If you take the output expression Y, then it is R1 plus C whole bar, 1 plus anything, 1 only, 1 bar, 0. That's it, guys. So for this given design, the output expression Y is always 0 only. This way, guys, again we are telling you, if you want to excel in VLSI industry and related things, you need to know about logic optimization, because VLSI means real estate. Each and every micron is also important to us. Hence, as good as possible, we need to minimize the logic design, and you need to implement the design as per the design challenges. Let's have another design challenge. This is the design, and we want to know the simplified output expression for the given design. What is Y? The simplified Boolean expression. And now, guys, what is the output of this gate? It is A into B. Similarly here, it is BC. And it is C. Therefore, ABC. And this one, it is AB XOR BC. Now the output expression for Y, it is ABC XOR AB XOR BC. Now guys, just like AND operation, OR operation, XOR operation is also there. Hence here we can take common, AB common. Hence it is AB C XOR 1. Again, this is as it is. Now guys, in a XOR gate operation, if one of the input is logic 1, it becomes like a inverter. It is complement of the another input. Therefore, here you get C bar. Hence it is ABC bar plus BC. This XOR operation. Now here, if you perform XOR operation, ABC bar whole bar BC plus ABC bar BC whole bar. This one, guys. Now here, when we simplify, it is A bar plus B bar plus C into BC plus ABC bar into B bar plus C bar. Now guys, here it is A bar BC, B into B bar 0, B into C, BC into C, BC, again B into B bar 0, and this is ABC bar. Now guys, BC is common, BC into A bar plus 1 plus ABC bar. Again here, anything plus 1, 1 only, hence it is BC plus ABC bar. Take B as common, then it is C plus AC bar. Again here, by using distribution theorem, you can rewrite it as C plus C bar into A plus C. You can write in this way by using distribution theorem. Anyway, C plus C bar becomes 1. Hence, here the final minimized Boolean expression is B into A plus C. So for the given design, the output expression is B into A plus C. Right guys? Again here, remember, in VLSI, you need to concentrate the design optimization, logic optimization, so that it occupies less space, it works for better for high frequencies, etc. reasons. Logic optimization is the very important concern in VLSI. Okay, let's have another design challenge. This is the design, and we want to find out the minimized output expression. Why? What is the Boolean expression? Guys, here, hope you know, all are NAND gates only. These are one input NAND gates. In the same, like similarly, like simply you can say it is a NOT gate. Please don't think it is some other gate. It is a NAND gate only, and where two inputs are from the same P only. Okay, now let's see. Guys, here, instead of going towards the output of the every logic gate, getting it and again doing NAND operation and all, for a 1 second, you just wait and have a good breathe, and then you see this. Guys, here, this whatever you are seeing, this is simply a OR gate using NAND gates. This is a OR gate only, isn't it? Yes. Therefore, the output is here P plus Q. If you go in detail, this is P bar, Q bar, P bar into Q bar, whole bar. You will get P bar whole bar plus Q bar whole bar, P plus Q only. Similarly, you take this. This is also same. That is R bar, like this is plus Q bar, means simply you can say R plus Q, because it is a OR gate only. Right? Now here again we have a NOT gate. This is P plus Q whole bar. This one R plus Q whole bar. Now here the final expression output Y. Coming to this, here it is a NAND gate only. Therefore, P plus Q whole bar into R plus Q, R plus S. Oh, sorry guys, this is S. This one. So that here R plus S whole bar. Again whole bar, then it could be like P plus Q bar whole bar plus R plus S bar whole bar, then it can be written as P plus Q plus R plus S. Hence guys, for this given design, which is in only in terms of NAND gates, the output simplified expression is here, it is P plus Q plus R plus S. Simply it is like logical addition of every input. There's a P plus Q plus R plus S. Let's have another design challenge. This is the design. We have one XOR gate, XNOR gate, AND gate. And what is the simplified output expression? Right? Now, guys, here, this XOR gate, output expression is X XOR Y. And this will be like X bar XOR Y, like X NOR Z. Here, like you can go like in a general procedure, like this X XOR Y is X bar Y plus XY bar, and again doing XNOR operation. Instead of that, you can go in a straight away procedure. Yes, let's assume this X XOR Y as P. Just let's assume. Now guys, here what is this? P XNOR Z, isn't it? Yes. Now, what is F? F is P into P XNOR Z. Now guys, here you just like expand P into P XNOR PZ. Again take P as common, therefore 1 XNOR Z. Guys, in XNOR operation, if one of the input is logic 1, then it acts like a buffer. Output is same as another input here, which is Z. Hence, here I can say it is PZ. But actually guys, what is P? It is X XOR Y. Hence, here we can say this X XOR Y into Z. Okay. Now, if you like consider the XOR operation, then we get X bar Y Z plus XY bar Z. This is the expression for the given Boolean function for the design. Okay guys, let's have another design challenge. This is the design and they are expecting the simplified output expression F. Okay, there are many logic gates and we want to find out the simplified output expression. Let's start. Guys, here what is this? NOR gate. Therefore we get A plus B whole bar. Again guys, if you go in a regular procedure, A plus B whole bar into A, again here A plus B whole bar into B, like that, it may take more time. If you want to optimize the time, then you need to be very clear on the Boolean algebra and simplified things. Now, here A plus B whole bar, how you can rewrite? Applying the De Morgan's theorem, A bar into B bar, na? Now, this is A. This is A bar into B bar. Now guys, this AND gate output, A into A bar into B bar, A into A bar, 0, 0 into B bar, 0, you'll get 0 here. This is 0. Similarly here, A bar into B bar into B, B into B bar, 0, this will be 0, right? So now here, this is 0, even this also 0. Now guys, this is C. Now it is 0 plus C whole bar. What is that? C bar. This is C bar. Anyway, this is 0, this one, and this is C bar. Again here C bar, C. Now guys, here 0 plus C bar whole bar, C. Again here C plus C bar whole bar, C plus C bar, 1 whole bar, 0, it is 0 now. And again here finally guys, it is 0 and it is C. Now this is a NOR gate, so C plus 0 whole bar. Now what it is guys? It is C bar. Hence guys, for this design, the output expression is F is equals to C bar. Guys, suppose if they ask you to implement, write down in terms of min terms. Yes, you got the Boolean function as C bar. But they are asking you to express the Boolean function in terms of min terms. Then how you can express? Guys, here it is C bar. Actually, the design contains 3 variables. This is a minimized expression and you want to build in terms of canonical SOP, standard SOP. Hence, here you can rewrite it as y is equals to A plus A bar into B plus B bar into C bar. This one guys, see, if the Boolean function is C bar only, if they are expecting the answer in terms of min terms, sigma m of like that, then you need to consider that into canonical form. Okay, now guys, here it is A, B, C bar, A, B bar, C bar, A bar, B, C bar, A bar, B bar, C bar. Now if you write down in terms of min terms, then guys, it is 0, 0, 0, 0. Again 0, 1, 1, 4. It is 0, 1, 0 means 2. This one 4. And this 1, 1, 0, 6. This one. So here the given design like optimized Boolean function is C bar. In terms of min terms, it is sigma m of 0, 2, 4, 6. This is the one. Let's have another design challenge. Yes, this is the given design. And they said, what is the output expression y when c is equals to 0? That's it. Now, here there is a NOT gate. Therefore, for this AND gate, the input will be C bar. Similarly here, for this you need to know these gates output. Let's start from here. This is A plus B whole bar. And this will be C. Hence, this is A plus B whole bar plus C. Whereas here it is AB. Now guys, here for this, let's assume this is P. Okay. Now guys, here what is P? It is A plus B whole bar plus C plus AB. That's it. Now if you take the output expression y, it will be like P into C bar whole bar. So that guys, here it is P bar plus C. Bar whole bar is C only. Now it is P bar plus C. What is P bar? This one. A plus B whole bar plus C plus AB whole bar plus C. Now guys, here by using De Morgan's theorem, A plus B bar whole bar into C bar into AB whole bar plus C. Okay guys, now for this expression, if you like expand, you'll get like A plus B into C bar into A bar plus B bar plus C. Now in the design there is a requirement, that is C is equals to 0. If C is equals to 0, 0 plus anything, and here it is 0 bar 1, hence the finalized expression is A plus B whole bar into A bar plus B bar. This one guys, it is in the POS form. Still, do you need this expression in terms of SOP? Then again you cross multiply, you multiply like A into A bar 0, A B bar plus B into A bar B, B into B bar 0. Hence the expression is AB bar plus A bar B. That's none other than XOR operation only. That is A XOR B. Remember guys, the XOR gate logic expression in SOP form is this, in POS form is this. Right? Remember guys, this is what here the output expression for this particular design when C is equal to 0. Logic optimization is very, very important in our journey. Right? Now for this given design, we need to find out the F. Guys, it is a little level 2 question. Remember, because for n number of gates, we need to provide the output expression. That's it. Okay, now you see this 1, 2, 3 and so on n. Guys, this AND OR gate combination is going to repeat like this. So it's better to calculate the output it here, and maybe if you take this again to one more OR gate, and this will be the fourth gate, and we need to find out this expression so that we will get a clarity regarding the 6th or 8th and nth gate. Okay, now let's start. First one, at the second gate, output. What will be the expression? That is x0 into x1 plus x2. Similarly guys, for the fourth gate, what is the expression? It is like x3 into x0 x1 plus x2 plus x4, because guys for this will be x4 only, the same x1 x2 x3, this will be x4, right? This is the one, and so on. Even if you want to write the 6th gate or 8th gate, yeah, just go ahead. Yes, you can go. But now here we want to tell the nth gate expression. Yes, that's another than output expression only. Now when you verify this from here, how you can write is, see the expression for n number of gates, that is simply guys, here it is like, see for this you just expand, it is x0 x1 x3 plus x2 x3 plus x4. Actually this is the fourth gate output, right? Isn't it? Yes. Now in the same way here for nth gate output, it will be like x0 x1 x3 and so on. For nth gate, for fourth gate you got x3. For nth gate obviously you will get here xn minus 1, because here for 3 na, plus x2 x3. Again guys, you can see here for fourth gate till x3 you got, hence x2 x3 and so on xn minus 1, because guys remember this is for nth gate, right? Now again plus for fourth gate x4, hence for nth gate xn, this one. So guys, for this given design, the logic expression for f means for n number of gates in this and or cascading fashion, the expression is x0 x1 x3 and so on xn minus 1 plus x2 x3 and so on xn minus 1 plus xn, right guys? Like these are the some tricky examples where it can cultivate your logical reasoning, right guys? Let's have a very good question on dependency. Yes, here coming to the input, there are 4 variables for this given design challenge in terms of the midterms. The output, is it dependent on all the variables or dependent on only one variable, 2 variables or 3 variables? That we want to find out. That's what the question in the lucified language. That's it. Okay, let's see. Consider the following Boolean function of 4 variables f of w, x, y, z is equal to sigma of 1, 3, 4, 6, 9, 11, 12, 14. The function is independent of 1 variable, 2 variable, 3 variables, all the 3 variables. Now guys, sometimes they may give you the logic diagram, the design. From the gates and all you need to get the expression. From that expression we can tell. But here in this model they have given the minterms. So what we have to do is, you get this expression, you simplify this. When you simplify, you will get the output expression. As per that we can tell. That's it. Okay. Now as there are 4 variables, we need 4 variable K-map. Hope you know how you get the 4 variable K-map. It is like this. Like this is Wx, Yz, W bar X bar, W bar X, Wx, Wx bar. Similarly, Y bar Z bar, Y bar Z, Yz, Yz bar. Okay. Now guys, here as per the numbers, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This one guys, we mapped into the K-map, graphical representation. Now if you want to simplify, there is a quad here. Similarly, there is a quad here. For this, the expression is Wx bar, W bar X bar. You will get X bar. And from here, Z. Similarly, for this quad, X and Z bar. Hence guys, the final expression F is equals to xz bar plus x bar z. This one. Now from this we can tell, as per the the minterms expression, the simplified output expression depends upon variable x, variable z, and their complements as well. It depends on x and z variables, and it is independent on the remaining 2 variables. What are they? W, y. So the simplified output expression does not contain any w or y variables. Hence we can say it is dependent on 2 variables and it is independent on 2 variables. As per the options, the right answer is option B, independent of 2 variables. Right guys? The dependency is also important so that we can come to the conclusion the output is exclusively dependent on those variables, etc. Right? Here again we are taking one more, the good design challenge. Yes, it is a design. In this design, one of the gate is redundant. What is that? We want to find out. That's it guys. That's what the question. We need to identify the gate which is redundant, not required. Unnecessarily they have taken. What is that? We need to find. Now coming to this guys, for this, what is f? If you write down the expression, this is x, y bar, z. This w bar, x, z. This w bar, y, z. Now guys, here if you take this one, it is like x, y bar, z plus w bar, x, z plus w bar, y, z. This is the one. It is in the simplified form, not in the canonical form. So here at this particular instant, if you take like any some variables are like what is that, common and all, instead of struggling here, it's better to convert this into canonical form and you can draw the K-map. Once you draw the K-map, you will understand in the best possible way. Hence, without any delay, we are entering into the K map. Yes. Now guys, as they said, 4 variable. Okay, of course, 4 logic gates. Like from this it is X, Y, Z, right? X, Y, Z, W. Hence we are telling it is a 4 variable K map. Okay, the 4 variable K map will be in this way, where we take Wx, Yz, W bar X bar, W bar X, Wx, Wx bar. Similarly here, Y bar Z bar, Y bar Z, YZ, YZ bar. Now guys, here you see XY bar means here you take Y bar Z. Here it is Y bar Z. And coming to the X, X is mandatory. You can take both W bar and W. Hence this will be 1, this will be 1. XY bar Z, W, W bar. Similarly, W bar X, this one. Z. Z means you can take this and this, means these two. Anyway here, so we can keep it as it is. Now the last one, W bar YZ. W bar YZ. YZ means here. So that here W bar means these two. So that you can take X and X bar, means already it is there. Here you need to take this one guys. So we mapped it. Now here if you simplify, you can take one pair here, you can take one pair here. Now guys, what is this? W bar YZ. Similarly this one, X Y bar Z. This one. Now guys, W bar YZ, this term is there. Similarly, X Y bar Z, this term is there. So what is left over? What is this? W bar XZ in a simplified format is not appeared. No need. Hence, this is the redundant term. Okay guys, and from where, from which gate we are getting this redundant term? None other than gate number 2. This one, this is W bar XZ is the redundant term. This gate is not necessary. You just remove this, you connect it as it is, so that you will get XY bar Z plus W bar YZ. This one. So in this way we can identify the redundant gate for any question, for any model. Remember, once you get the finalized expression, you just simplify. Either you take for Boolean algebra or K-map. It's up to you. Mostly it's better to go with K-map. It's a graphical representation. No need to put more efforts. Remember guys, once you get the simplified expression, now you compare with the original initial expression, so that we can easily identify which gate is redundant, which gate is not required. Okay guys, we are going to discuss about the design challenges with respect to functions. Yes, instead of giving the inputs, just like a variable A, B, C, P, Q, R, here the inputs are functions. And what will be the output function, or any one of the input function by giving the output function. There are different kind of models in this particular topic. Okay, without any delay, let's enter into the question. Consider 4 variables functions f1, f2, f3, which are expressed in sum of minterms as f1 is equal to sigma of 0, 2, 5, 8, 14, f2 sigma of 2, 3, 6, 8, 14, 15, f3 sigma of 2, 7, 11, 14. For the following circuit, the output can be expressed as this one guys. For this, you need to know about Venn diagrams knowledge. Once you understand the Boolean algebra Venn diagrams concept, it is so easy to handle this question without any delay, without any strugglings. Yes, and for better understanding, we are giving you the link in the description regarding the Boolean algebra Venn diagrams concepts. once you go through it, so that you can understand and you can challenge any kind of question similar to this very easily. Right? Now, let's see, guys, coming to this F, what it is? This is a AND gate. It is F1 into F2. And this will be F3. Now, guys, here the expression is F1, F2, XOR F3. Isn't it, guys? Now, coming to the AND operation. Guys, if it is F1 into F2, that means, exactly speaking, that is F1 and F2 only. Okay, exactly speaking, it is not F1 into F2. It is F1 and F2. Remember. Now, if you take the Venn diagrams concept, then obviously, guys, if there are two variables and we want to take, let's assume this is F1, this is F2, and you want to know F1 and F2, what portion we need to consider? This one, the common portion only, F1 and F2 only now. Similarly, if it is F1 or F2, we will take A union B. F1 union F2 means everything regarding F1 and F2. So here remember, F1 and F2 represents the common portion present in both function F1 and function F2. Therefore, you see here, that is F1 and F2. What are the common minterms here? 2, 14, isn't it? Of course, 8 as well. 2, 8, 14. Hence, F1 and F2, which is F1 into F2, is sigma of 2, 8, 14. Got it? Similarly, let's assume this is F1, F2 and we need to do XOR operation. Again, guys, you take one XOR operation. Let's assume this is A, this is B, A, B. Then, guys, what is A XOR B? That is A bar B plus AB bar. Where you get A bar B, guys? Here only, na? Similarly, A B bar. Of course, this is A bar, like A B bar, this one, and that will be A bar B. This one, guys. So, in the Venn diagram from this, what you can analyze is, in this Venn diagram, XOR operation means you need to separate the common terms and remaining terms you have to take. That is what XOR operation. Here A is there, B is there. You are not taking the common terms. Other than the common terms present in both A and B, we are taking. The same analysis now you have to apply. Now, guys, this is F3. This is the resultant 2, 8, 14. Now what to do? We need to follow XOR operation now. For XOR operation, the common terms you need to exclude and the remaining terms present in both the functions we need to consider. That's it. It is so easy. Okay. Now let's see here. It is common terms 2, 14, 2, 14. Then obviously exclude them. Hence here F will be sigma of the remaining terms 7, 8, 11. 7, 8, 11, guys. That's it. Once you understand XOR operation through Venn diagram, AND operation, even OR operation also. If there is a OR operation, you need to consider all the terms, because A union B is A or B, no? A and B is A intersection B. For that I have told you, for this you need to have Boolean algebra, Venn diagrams concept. You check it in the description, you will get the link so that you can understand very clearly. Right guys, this is what here the identification of the function in terms of minterms for a given functions which are present in the minterms. Right? Let's have another design challenge. Yes, this is a given design. The inputs are in terms of functions, not variables, functions. And in this design, they have given the output function also. But we want to identify, we want to determine F3 function. What are the minterms present in this? That's it. That's what the question. Now in this question, the approach is like, finally you need to get the output expression first. As per that, you can do either AND operation, XOR operation, or OR operation, etc. So let's find out the output expression F in terms of F1, F2, F3. Guys, here it is F1 into F2 whole bar and this F3 bar. Then obviously F is equals to F1 into F2 whole bar into F3 bar whole bar. By applying the De Morgan's theorem, you can rewrite it as F1 into F2 bar whole bar plus F3 bar whole bar. Then guys, the output expression is F1 into F2 plus F3. Okay, now guys, here F1 into F2, what it means? It is AND operation. Remember guys, F1 into F2 is F1 and F2. So here, for better understanding, you need to know about Boolean algebra Venn diagrams concept. Hence we have given the link in the description. You can go and check, and you watch the video, you will get a clear understandings. Again I am telling you, if it is F1 into F2, consider AND operation. If it is F1 plus F2, consider OR operation. Right? Even the same model, there is a similar model also, that also we are giving in the description. You can watch the same numerical model in a different way using XOR gate. Okay, let's enter into the solution. It is F1 into F2. We need to follow AND operation. These two, AND operation means it is A intersection B. If it is A intersection B, we need to consider the common terms present in both the function. The common terms are only 5. Hence guys, it is sigma 5. Okay, and the output function is also given, that is F1 F sigma of 1 4 5. Then what might be the F3? Therefore we will get the output expression in terms of minterms as 1 4 5. Guys, here we need to find out this F3 now. Anyway we have 5. It is plus means OR operation. If it is OR operation, we need to consider A union B. Okay, so here we need 1 4 5. Anyway 5 is present, then the F3 must be either 1 4 or it must be even F3 sigma of 1 comma 4 comma 5. It could be in any way, because see, it is OR operation. We'll take A union B. If it is sigma 5 plus sigma of 1 comma 4, you will get 1 comma 4 comma 5 only, na? Or else if F3 refers 1 comma 4 comma 5, then 1 comma 4 comma 5 union sigma of 5 repeated, so what, will take only one time, then it is sigma of 1 comma 4 comma 5, this one. Hence in the broader way we can conclude that for the given input functions f1 and f2 and f. In this way, the f3 function must be sigma of 1 comma 4 comma 5. You can take 1 comma 4 also, but here we are like giving in the broader way, that's a 1 comma 4 comma 5. This is what here the input function f3 as per this design. You need Boolean algebra concept in Venn diagrams concept in Boolean algebra, must and should, right? So this is what here the regarding the design inputs combinations identification. Again a design challenge. Yes, what is that? Let's see in the design shown below. Will LED glow or not? If yes, explain how. If not, explain why. Guys, this is the design. We have AND gate, XOR gate, NAND gate. There is an LED here, which is a light transmitting device. Of course, it contains 4 1 kilo ohm resistances. There are 2 switches here, S1, S2. Whether LED glow or not, or is it permanently off, that we want to find out. That's it. That is itself is the challenge. Okay. Now, as per the switches, let's try. Let's consider here S1, S2. The switches can be on or it could be off as well. And for better understanding, let's assume A, B, Y. The AND gate output, XOR gate output, NAND gate output. A, B, Y. Okay guys. Now let's assume S1, S2 both are off. If both are off, they act like a open circuit. Then this 5 volts will appear here. This here also 5 volts will appear here. Then the AND gate output becomes logic 1 because 1, 1, 1 into 1, 1 only. Hence the output of AND gate is logic 1. Similarly, B. You take here the output. Anyway, this becomes logic 0 only because it's an open circuit only, na? And here this one becomes 5 volts. And this will be 5 volts through this. Hence, it's a 5, 5. Like 1 XOR 1. It becomes logic 0. Hence, this Y, NAND gate, 1 into 0, 0, 0 bar, 1. If it is 1 guys, means for this light emitting diode, anode side 5 volts, even cathode side which is Y also 5 volts, then will LED glow? No. The anode side voltage must be more than the cathode side voltage. Then only LED will glow, right? So the voltages are same. Then current cannot flow, LED will not glow. So that we can say the LED will be in off state only. Similarly, let's take off, on. If it is off guys, here you will get 5 volts because S1 is off and S2 is on. Guys, if S2 is on, short circuit, then definitely this will be 0, this will be 0, isn't it? Yes, so the same 0 here, and this will be like through this. This is permanently 1 only. This one is permanently 1. So that here this is 0, then it's a logic 1. 1 into 0, 0, 0, 1, 1. Then guys, here for the NAND gate, 0 into 1, 0, 0 bar, 1. If it is 1, LED will be off only. Similarly, let's take on, off. Therefore guys, here if it is on, this will be short circuit. If it is short circuit, here you will get 0. And S2 is off. Then here you will get logic 1. Here also you get logic 1. Because through this. Now guys, 0 into 1, 0. 1, 1. It's XOR operation. 0, 0 into 0, 0, 0 bar. 1. Again LED will be in off state only. Let's try the last state, on. Both are on. If both are on, here it acts like a short circuit. Switch is on. Here you get 0. Here also you get 0. Because of this, here also you get 0. This is permanently 1 only. 0 into 0, 0. 0 into 1, like 0 XOR 1, 1. Then 0 into 1, 0. 0 bar, 1. That means even when both the switches are on, then also LED will not glow. Hence guys, what we can tell through this table is here the LED permanently in off position only, off state only for this given design. When you take the switches, both are on, both are off, on and off, but still the output is always 1. Hence LED will not glow. It is always in reverse bias only. Okay guys, this is what the design challenge. Thanks for watching. See you in the next video. This is Shivram signing off. Jai Hind.